All right, hi everyone. I'm John. I'm going to build on two of the previous lectures. So first, Andre's lecture and Peter's lecture from earlier, where he talked about actor-critic methods. So I'm going to talk about more advanced optimization methods to use along with policy gradients. So what Andre just talked about in the last lecture could be called a vanilla policy gradient method, because it's essentially just getting a policy gradient estimate and plugging it into stochastic gradient descent. And there are various ways of modifying that and bells and whistles you can add. Like Peter talked a lot about these actor-critic methods that use the value function to get a lower variance advantage estimate. So you can do a lot to get better advantage estimates, but I'm actually not going to talk about how to get better advantage estimates. I'm going to talk more about changing the underlying optimization algorithm. Once you compute your advantage estimate, how do you update the policy with that? And so I'm going to, and essentially this is for two reasons. There are two things we need to improve on from the vanilla policy gradient methods. One issue is that it's pretty hard to choose good step sizes for them and to choose a single step size that's going to work over the course of the whole optimization process. So, I mean, in reinforcement learning, one difference from supervised learning is that the data that your network is receiving as input is non-stationary. And that's because as your policy changes, you see a different distribution of observations and rewards. So that means, so you might, for example, be getting 0 reward for a while, and then at a certain point, your policy randomly gets a positive reward, and then your reward starts going up. So what that means is that the statistics of your inputs are changing over time. So it's hard, that makes it particularly hard to choose a good step size, which is going to work over the whole course of the learning process. And you can address that somewhat by normalization techniques, but it remains a problem. So another issue with the step size is that if you take too big of a step or a bad step, this is more damaging in the reinforcement learning setting than it is in the supervised learning setting, because if you mess up your policy, then you're going to start collecting bad data. Like if you change your policy by too much, then you're going to visit a totally different part of state space. You'll have a bad policy, and then you won't be able to recover because all the data you're seeing from that point forward is from this bad state distribution. So you can have a disastrous drop in performance if you take a bad step. This makes it really hard to design a nice and stable algorithm. Another issue with the vanilla policy gradient methods is their sample efficiency. If you just, when you collect some data, if you just use them to compute a single gradient and then throw the data away, you're probably not getting all of the available information out of it. And you can see that especially well if you imagine that your network is scaled poorly. Like, let's say some of the gradients are 10 to the 5 times bigger than other gradients. I mean, gradients on some components are bigger than the gradients on other components. Then you're going to make very little progress on the ones that have tiny gradients if you're just doing normal stochastic gradient descent. So you might, so anyway, you might have really slow learning, and we might be able to do better at this by using a more sophisticated kind of optimization method that instead of just taking a single gradient with the data, you can solve some little optimization problem whenever data comes in. So I want to make that point in a slightly more philosophical way, or describe what we kind of want to do here. So if you think about a lot of modern machine learning, a lot of it's about reducing the learning problem to numerical optimization. So learning is about being able to make some kind of prediction on data you haven't seen before. And what deep learning is all about is writing down some kind of numerical optimization problem and then using some kind of gradient descent algorithm to approximately solve it. And in supervised learning, you're just minimizing training error. And what you really care about is test error, but if you minimize training error, that's usually pretty good, especially if you tweak regularization and things like that. So in RL, it's, the situation is not as clear-cut. So we'd like to write down some kind of optimization problem we can solve, which uses all available data that we've seen so far and computes the best policy from that, but it's not clear how to do that. What optimization problem should we write down? So Q-learning is actually quite nice because you can take any set of transitions from your dynamics model and you can fit a Q function using them. You can try to fit Q star because the Bellman equation makes sense no matter what policy your data was sampled from. So that's pretty nice, but this comes at a cost of actually optimizing the wrong objective. So in Q-learning, you're trying to minimize some kind of Bellman error when what you really care about is that your policy performs well. So policy gradient methods are, in contrast, actually optimizing the thing you care about, which is the performance of the policy. But the downside is that they're not as good at using old data or at using all the data you have available. So this lecture is going to improve a little bit on the vanilla policy gradient methods, where instead of just taking our gradient estimate and taking one step with that, we're going to actually write down a little optimization problem based on the data you collected from your current policy, and we're going to solve that optimization problem approximately. So we get a little bit more information out of our data this way. It's still not perfect because you can't take all the data you ever collected, but it's an improvement. So then the next question is, what loss should we be optimizing? So we want to write down some kind of loss function to define a policy gradient method, but what kind of loss should we use? So first, let's just look at our vanilla policy gradient formula. So here we have, this is just one way of writing it. We have some kind of expectation. The hat means this is an empirical expectation, meaning we collected a bunch of time steps and we're averaging over them, so we're averaging over t. And we take grad log probability of the action times the advantage. Okay, so that's our policy gradient formula. And well, we can write down a loss function such that differentiating that gives us the policy gradient. And the loss function we want to write down, one choice is we just write down log probability times advantage estimate, which is treated as a constant. So obviously, if you take the gradient of that, you get our policy gradient estimate. And this is actually what you want to do if you want to implement policy gradients with an autodiff library. What you should do is just write down this loss and then differentiate it. Okay, but the thing about this loss is it doesn't actually make sense as a loss that you can do many optimization steps on. You don't want to optimize this to convergence because let's say the advantage is positive. Then you're going to try to drive the log probability to infinity, or you're going to drive, well, if it's a discrete action space, you're going to try to drive the probability to 1 for that action. Or if the advantage is negative, you're going to drive the probability to 0. But the advantage estimate is noisy, so so you might have just gotten a noisy estimate, and you're going to radically change your policy based on that, and that's probably going to make your policy worse. So this clearly isn't exactly right. Well, I'm not going to fix that problem yet, but I'm going to say there's another version of this that's also interesting to look at and gives us the same policy gradient estimate. So instead of writing it as log probability times advantage, we can write it as this probability ratio times advantage. So if we write down this ratio and then we differentiate that, we get the exact same gradient. And that's just because of the chain rule. So if you have grad log of some function, the gradient is just grad of the function divided by the function value. So anyway, this formula is just as good. But this formula has an interesting interpretation in terms of importance sampling. So one thing that's pretty sensible to do is to say, we're going to sample, okay, we're going to collect data from some policy, which I'm going to call pi sub theta old. And then we want to, then let's say our new policy, which means our updated policy is called pi sub theta. So one sensible thing to do is we want pi sub theta to have high expected advantage. So we want like policy pi sub theta to take positive advantage actions. So we write down this expectation, and then we do importance sampling. So in importance sampling, importance sampling lets you say, what would the expectation be under one distribution, even though I collected samples from some other distribution. So anyway, you can do importance sampling, and then you arrive at this formula I wrote on the previous slide. So it basically says we want to choose a policy pi sub theta such that the expected advantage under that policy is high, where we still are collecting states from the old policy, theta old. Anyway, I don't want to get too bogged down on this. But anyway, this doesn't solve the problem, which is that we want the policy update to be small. So that's the big problem so far. I mean, we can take a gradient step on that, and if it's a small step, we're okay. But the big problem is that we don't want to optimize this objective fully, because then we're going to do too big of an update. So here's a way to solve that issue. So the way to solve it is to use what's called a trust region. This is a well-known kind of method in optimization where you say, I have a function I want to optimize, and I have some local approximation of this function which is accurate locally, but it gets really inaccurate if you go far away from your starting point. So we have some kind of trust region where we trust our local approximation, and as long as we're in the trust region, we're willing to optimize our local approximation a lot. But if we get outside of that, all bets are off. So the way these kind of methods work is you say, I want to optimize this objective, which is our local approximation, subject to some constraint that we're not moving too far away from the starting point. And there are lots of ways we could define this constraint. For example, we could say that the Euclidean distance between our starting point, theta old, and our final point, theta, is small. So that would be one way to do it. But instead of using Euclidean distance, we're going to compute the KL divergence between the old policy, pi sub theta old, and the new policy, pi sub theta. So that's what we mean by this KL expression here. So this is just a distance. This just is a way of measuring the distance between probability distributions. So the nice thing here is we're actually looking at the distributions that the parameter vectors determine, as opposed to just looking at the parameter vector, where it's not clear what's a sensible update in parameter space, like how big of an update should we do in terms of Euclidean distance. That's pretty hard to say because we have some really complicated function that's going from the parameter space to the output space. But in terms of KL divergence is a unitless quantity, and it has a nice interpretation. So we're basically saying that the probabilities shouldn't change too much. The action probabilities shouldn't change too much. And so that's something that's that's very robust, and it's not problem dependent. So we can define some hyperparameters that make sense over a wide range of problems. So anyway, what we do is we say, recall that this expression just gives us the policy gradient. So if you differentiate this objective, it's just going to give you the policy gradient. Yeah, I mean, this comes out of some theory, but actually it doesn't make a difference in practice. So yeah, I mean, you can actually we're going to do an approximation later to the KL, and it actually the ordering doesn't really matter. Okay, so anyway, this is the constrained optimization problem we want to solve. And it's also worth considering that we could solve a penalized optimization problem instead of the constrained problem. So we could have said, let's just penalize the KL divergence instead of putting a hard constraint on it. And according to the method of Lagrange multipliers, this is essentially equivalent in that if we want to solve this problem, the solution it's a necessary condition that it's also the solution to this problem. Let's see, I had a couple of questions. Oh yeah, so the question was, have people tried to use different distances like Wasserstein distance and so forth, which have been used for GANs. So actually it isn't going to make that big of a difference what distance you use here, because usually we use pretty simple distributions over actions. So any kind of distance on probability distributions is going to do the same thing. Like, there's not too much to say about different distances between Gaussian distributions. If you started to use more sophisticated distributions, then that might be relevant. Another question?
So is the motivation for the data penalty just to enable, if there is some optimized space outside of the
Oh yeah, so the question is, why use the penalty instead of like the hard constraint? Actually, I'm going to talk about the trade-offs between these two things later. I'm just saying here that it's equivalent in a certain sense because we can choose some beta so that the solution for any given like hard constraint, we can get the same result by using the penalty. Okay, I'm going to move on. So anyway, so it turns out that there's actually a theory result that pertains to this penalized objective. So it's not exactly the version I wrote down on the previous slide, but if you take a max over state space instead of a mean over state space, and so you constrain the max KL between the new policy and the old policy over all of state space, then it turns out that you get something that's actually a lower bound on the performance of the policy, pi sub theta. So the point is, let's say we sampled some data with pi sub theta old, and now we want to get a new policy, pi sub theta. So we want to write down some objective such that if we maximize that objective, it'll actually improve the performance of the policy. So it's not totally obvious how to do that, because if we just take some approximation to, I mean, we don't have analytic access to the performance of the policy, because to calculate the performance, you need to interact with the environment. So we just want to write down some kind of objective that we can do numerical optimization on and doesn't involve interacting with the environment. And it's not clear that we can do this. But it turns out that that we actually can write down an objective which is a lower bound on the performance of the policy. And that involves a max of the KL over state space. And if we maximize that, then we're guaranteed to improve the policy. And we can illustrate that with this diagram here. So let's say eta, this red curve, is the actual performance of the policy parameter theta. Then if we compute this surrogate loss, which is the thing before we added the constraint or the penalty, then, okay, this is a good local approximation, which has the same gradient. But then if you go too far away, all bets are off. Like if we try to maximize that, we'll go all the way over here. So then if we add in the penalty, we end up with this blue curve, which now becomes a lower bound on the performance. So if we maximize this blue curve, we end up over here. And since it's a lower bound, that means that we're going to make more improvement on the real thing than we did on the lower bound. So we're guaranteed to make at least as much improvement on the real performance if we optimize this lower bound. So that's pretty nice that we can actually take some kind of non-trivial policy update and be guaranteed to do an improvement to the policy. In practice, the theory, we have to make some approximations of the theory because it's way too conservative in how, like, what kind of update it tells you to do. It tells you to do way too tiny of an update. So we use the mean of the KL over state space instead of the max KL, and we also, let's see, we do an empirical, a sample-based approximation to it, and we also take a bigger step than the theory recommends. So anyway, putting this all together in pseudocode, the way it looks is each iteration, first you sample a bunch of data from your policy. So you run your policy for t time steps or n trajectories. This is using your current policy parameter. Now we go back and look at all of our trajectories or trajectory pieces, and we go and compute the advantage function at all time steps. So then we've got this advantage function, and then we write down our constrained optimization problem, which is maximize this surrogate loss subject to some constraint. And then it turns out we can solve this constrained optimization problem efficiently using conjugate gradient. And I'm going to describe how to do that later. we can solve it approximately. We're not solving it exactly. And then we repeat. So this is an iterative process. And this is similar to some other methods like natural policy gradient and natural actor critic and reps. So this idea has resurfaced many times and will continue to. So now I'm just gonna, I'm gonna talk a little bit more about how you do this efficient solution using conjugate gradient. So this is actually not new to this method, TRPO. This is, these are some kind of well-established methods from numerical optimization. The idea is that you have some kind of problem, nonlinear optimization problem you want to solve. So what you do is you repeatedly make an approximation to it and then solve that subproblem. So we're going to make a pretty aggressive approximation to this, the nonlinear optimization problem, where we make a quadratic approximation to the constraint and a linear approximation to the objective. And we solve these quadratic programs, and then we do that efficiently. But anyway, let's just look at the penalized version of the problem and look at how to solve the penalized version. So first we're going to make a linear approximation to the objective and a quadratic approximation to the KL constraint. Note that the KL constraint kind of just looks like a quadratic distance function. So the KL divergence has, well, it has zero derivative at your starting point because it's minimized at your starting point. So the KL has two arguments. It's like a distance between two probability distributions. And the distance is minimized. If you look at varying one of the arguments and keeping the other one fixed, the distance is minimized when you're at the starting point, and it goes up smoothly as you go away from it. So it looks like a kind of quadratic distance function. But we want to figure out exactly what the matrix is that defines this quadratic distance function. So we're going to make this approximation to the problem, and this is just the Taylor series kind of expansion to second order around theta old. And okay, and these are, so we want to make this linear, this affine approximation of the objective and quadratic approximation of the constraint, and that's because it turns out that, well, I won't go into all the justifications. And anyway, the solution to this is just like it's just a constant multiple times this matrix F inverse. That's F is our Hessian times G, which is the gradient. So as it turns out, the F here is called the Fisher information matrix. This is something that appears all over the place in probability theory. It's sort of telling you how sensitive the probability distribution is to different directions in parameter space. So it's telling you if I move in this direction in parameter space, how big of a change to the probability distribution is that. So anyway, this step that you get when you solve this quadratic program is called the natural policy gradient. So anyway, we somehow, okay, this is all well and good, but we don't want to compute this, we don't want to compute the whole Hessian because it's really expensive to compute a Hessian. Like computing the gradient of some scalar valued function is only a small multiple times the computation cost of computing the function itself. That's a kind of the principle, the cheap gradient principle it's called. But computing the Hessian is way more expensive. It's effectively, you have to compute n gradients if you have n parameters. So that's really bad. So yeah, we could go ahead and compute this Hessian, but it would be really expensive. So, okay, anyway, I'll skip this because it's not that important. Okay, I had a section on the, I must have deleted that slide by accident. That's funny, I had a nice slide. Okay, anyway, what I was going to say is that you can, you can actually compute this, this expression F inverse G without actually ever explicitly forming the matrix F. And this is a pretty neat idea, and this is using the conjugate gradient algorithm. Well, you can the conjugate gradient algorithm is a way of approximately solving linear equations. So in this case, the linear equation we want to solve is fx equals g. So conjugate gradient algorithm will approximately solve this linear equation without ever explicitly forming the matrix F. Instead, it just needs to take a bunch of matrix vector products. You just need to define some function that takes a vector and it computes f times x. And then you call that function a bunch of times, like 10 times, and conjugate gradient algorithm will approximately solve this equation. And as it turns out, okay, so how do we get this function that does the matrix vector product f times x? Well, it turns out if you have a regular old reverse mode autodiff program like TensorFlow, you can do that. And you can just write down the gradient vector product, and then you differentiate that to get a Hessian vector product. So anyway, you can check out the textbook Numerical Optimization by Nosidal and Wright, which has a really good explanation of this idea, which is used a lot in nonlinear optimization. So that's what we use here. It sort of appeared in the deep learning community called Hessian-free optimization maybe 5 years back or so. And then it was used in the trust region policy optimization in the deep RL setting. So anyway, that's what TRPO is. Let's see, do I have a slide of that? Okay, anyway, I already showed you this pseudocode for TRPO. So let's see. Okay, so a summary of what I just showed you is, okay, we want to optimize, okay, we wanted to write down an optimization problem which we can solve to do a policy update. And this way we'll get a more sample efficient and more robust algorithm than the vanilla policy gradient method. So we want to write down some optimization problem. So the first suggestion is to just write down some kind of loss that when you differentiate it, you get the policy gradient. So we got this LPG, which was just log probability times advantage, and LIS, that's for importance sampling, which is like this probability ratio times the advantage. But that's no good because it doesn't actually constrain the size of your update in any way. So instead, we suggested to use the KL divergence to constrain the size of the update. But then we have a constrained optimization problem, which is harder than just solving an unconstrained problem. So we suggested instead, so we noted that when you do a quadratic and affine approximation to this problem, you get the update step looks like F inverse G, this is the Fisher information matrix, and this is the policy gradient. This is the same as something that was proposed previously called the natural policy gradient. And we can solve for this step approximately using the conjugate gradient method. And TRPO also does a line search on the original constrained optimization problem to make sure that the update that you did is actually a good, improves the objective in that constrained optimization problem. Yeah. 10 minutes, okay. Okay, that's fine. So let's see. So there's also another version of this that's worth knowing about, which is in which you don't actually use the conjugate gradient algorithm, but instead you directly look at the penalized version of the objective. And this is useful if you either don't want to do the conjugate gradient algorithm because it doesn't work in some setting, or I don't know, in some cases this might work better. But anyway, the idea is we're going to work directly with our penalized objective, and then our pseudocode is that we first collect data from our policy, we estimate the advantage function, and then we just do SGD or LBFGS, just any old unconstrained optimization algorithm on this objective with the KL penalty. So that's an easy thing to do, but the problem is it's hard to choose this coefficient beta in a way that it works well over the whole course of the optimization. So what we can do is we can instead just choose the KL divergence as our hyperparameter. And what we do is we adjust our penalty coefficient beta to try to make the constraint satisfied exactly and tightly. So basically, if we took too small of a step, so after we did our optimization, if our step was too small, we reduced the penalty coefficient. And if the step was too big, we increase the penalty coefficient. So we're not going to exactly get the right step every time, but since each step is pretty small, it's not that bad. And over time, I mean, over the whole course of the optimization, we'll basically stick to the right KL size. Actually, I see a lot of hands, but I'm pretty low on time, so I just want to get through a lot of my slides in the next 10 minutes, and then I'll get to the questions. Okay, so it's also worth looking at what's the connection between the trust region problem we're solving in TRPO and other reinforcement learning methods. So, okay, as I said in the last slide, if we do this linear quadratic approximation, we get the natural policy gradient. If we do no constraint at all, then this is just normal policy iteration. That might not be totally obvious, but if you look at what policy iteration is doing, it's just, you're just you're choosing a deterministic policy each iteration in which you choose the action that had the highest advantage according to the previous policy. So if you have no constraint at all, it's just policy iteration. And if you use a Euclidean distance to constrain your step instead of using a KL divergence, and then we do the linear quadratic approximation again, then we end up with just the vanilla policy gradient. That's you can just write it, go through the logic, and you'll come out with that result. So okay, this has some limitations though. So one issue is that it's hard to use in architectures that have multiple outputs. Like if you have, if the policy is outputting action probabilities and a value function, then it's not clear what you should use instead of the KL divergence, because the KL divergence doesn't tell you anything about how you should update your value function part. Empirically, it performs kind of poorly on tasks involving deep convolutional neural nets and RNNs, at least on certain benchmark problems, like the Atari benchmark. So I don't know exactly why this is true, but it might have to do with the first thing, but that's not the full explanation. And third, the conjugate gradient makes it a little bit less flexible than if you just had to do SGD, and it makes it more complicated. So I want to talk about two alternatives to TRPO that do something similar in that you do something like the policy gradient update, but you do a more sophisticated kind of update step, and you're trying to constrain the size of the update. But I'm going to talk about two alternative ways of constraining the size of the update. So first way is there's this method called KFAC, which is actually pretty recent, but the idea here is we can make an approximation to the Fisher information matrix, which actually exploits the structure of a neural network. So in particular, you find some kind of block diagonal approximation to this matrix, where each weight matrix in the neural net is treated as its own block of parameters, and then you assume a certain kind of factorization. You assume that this block has a factorization as a tensor product of two other matrices. So it's actually quite simple. You assume that there's an alternative expression for the Fisher information matrix as an expectation of outer products of grad log probability. So then you write out what's the, okay, you look at, actually I'm kind of running out of time, so I'm not going to go through all the details. But anyway, you write down what the actual Fisher information matrix is, this expectation, which involves a product of four things, and then you just assume that it factorizes as, you assume the two things are independent, and then you have some factorization, and this lets you, this is actually lets you efficiently compute and estimate this, an approximation to the Fisher information matrix. Using this approximation of the inverse Fisher matrix, you can do a natural gradient step in the same manner that we described previously. And all you have to do extra computationally is you have to maintain running estimates of a couple of covariance matrices, and then you periodically compute inverses of these matrices. There's an algorithm proposed or published a couple weeks ago called ACKTR, which combines this KFAC idea with A2C, basically plugs in the KFAC natural gradient into the actor-critic algorithm, A2C, which is like A3C, but without the asynchrony part. And it's basically a pretty small amount of overhead on it, but it works a lot better. The limitations are it's less straightforward to use when you have parameters being used multiple times and with recurrent neural nets, but it can probably be used in these cases also with a little bit of extra work. Another algorithm is proximal policy optimization. That's what I just described before, where you use the penalty instead of the constraint. As it turns out, this version I described before with the adaptive penalty is okay, but it's not the best possible thing. And something that works even better is to write out a certain kind of objective that involves writing down this importance ratio like we did before, but clipping it so that it doesn't go. So you're basically saying, I don't want to change the probability ratio too far away from 1. But that itself wouldn't be exactly right, because then you wouldn't any longer be optimizing a lower bound or pessimistic bound on the policy performance. So what we do instead is write down a certain kind of element-wise minimum between the clipped objective and the unclipped objective. I'm low on time, so I'm not going to be able to explain it fully, but basically it's another kind of lower bound objective, which empirically works pretty well. And you just, this is a pretty easy thing to implement, because you just write down your vanilla policy gradient implementation, but then you switch to this weird looking objective and optimize that for many steps of gradient descent instead of just one step. And that way you're getting more information out of your data. And you're doing an update that's actually kind of achieves a reliable amount of KL divergence between the new policy and the old policy. So yeah, anyway, this pretty simple pseudocode. It's a lot better. Well, it's a bit better than TRPO on continuous control problems like these robotics control problems. And it's a lot better on these image-based problems like Atari, where TRPO was really bad on those compared to A2C, whereas PPO does better, as does ACKTR from the previous slide. And it's compatible with RNNs and multi-output networks. Okay, I'll send out the slides, so here are some extra citations on the stuff from this slide. Let me actually just show you a cool video, because everyone likes cool videos. So here's a policy. We had a OpenAI blog post for this algorithm PPO, and we trained this humanoid to run around. Actually, you can. This environment is available in the repository called RoboSchool, so you can actually do this yourself. And we also released the code for PPO, so you can. You can train a policy to do this yourself, though we didn't release the exact training code for this because it was messy. Anyway, you see that this guy is trying to run towards the red ball, which gets randomly placed around it every 10 seconds or every few seconds. And meanwhile, it's getting pelted by these cubes, which are being thrown at it. And it's able to get up off the ground and also steer towards the red ball. It's not perfect, so it can't, sometimes it gets stuck on the ground for a few seconds and so on, but it's actually pretty good. And it can recover from getting hit in all sorts of ways. And yeah. So yeah, I don't know, that's up to you to decide. I think there's some interesting questions there. Let's see. Oh yeah, when we do it without the pelting, then it can actually basically run perfectly and it never falls over. With the pelting, it's a little harder, so it's not always perfect. But this guy can turn on a dime. It's actually quite nice. Oh yeah, we can also, after we train that policy, we can just, I just wrote a little script that would control the ball with the keyboard. And then even though this is a little bit out of sample because we never trained it for this exact distribution of tasks, it can do this perfectly well and run around when you control it with the keyboard. So you can imagine some video game where it's actually fully physical and everything. You can also use this on a more realistic looking robot like the Atlas robot. So this was all these really cool results are from my colleague Oleg, who trained all these crazy policies. Okay, we also have a blog post recently on this ACKTR method I was talking about. And we have some code we have some code for a bunch of these things. Like we have A2C, ACKTR, DDPG, DQN, PPO, and TRPO. I'm going to add some more tests to it, and it's some more documentation, but it's up there, so you can use it if you're willing to dig into the code a little bit. To train, actually, the humanoid who's running around and getting pelted by things, I think that was less than a day to train it on one machine that had about 32 cores. Yeah. Okay, so I'm wrapping up. Let's see. Yeah, that's all. Questions? Thank you.